Okay, so we covered Ka last day. Now we're going to look into Kb, which is looking at bases instead of acids when they're weak. Now, spoiler, this is incredibly similar to Ka, except that A's are now turned to B's and hydronium is hydroxide. But there is an extra step that often we need to actually find the base ionization constant, right? The Kb value, because we don't have that in our data booklet. We have Ka's in our data booklet. So we have to find a Kb and then use that. So just as review, remembering that ionic hydroxides are strong bases and associate quantitatively. So it's not for ionic hydroxides. We're doing this for weak bases. Okay, so and if we look at our data booklet, of course, hydroxide is at the very bottom. My OH minus, that is my only strong base. So let's get into weak bases. So here, well, no, let's first of all, I guess, do an example. I forgot that I had this in here. Of doing a hydroxide concentration for sodium hydroxide, which would be a strong base. This is a hydroxide solution. So first of all, let's realize that if I take NaOH aqueous, it dissociates into sodium ions and hydroxide ions. So if I wanted to find the hydroxide ion concentration for this, and the sodium hydroxide solution is 0.445 moles per liter. Well, this is really simple. All I'm doing is saying, well, hydroxide concentration then is equal to 0.445 moles per liter for NaOH multiplied by 1 hydroxide divided by 1 NaOH aqueous gets me, 1 second, Harlow, let me finish this question, 0.445 moles per liter for the strong base. Okay, so now getting into weak bases. For weak bases, Kb is my base ionization constant, just like Ka was my acid ionization constant. So for example, if I have this kind of weak base reaction of propanoate ion, something like that, reacting with water to make propanoic acid and hydroxide, and ask what is the Kb expression? Well, we can kind of write that out, and I wish I would have picked a base that was a little bit less in terms of letters, but it is what it is. So Kb is C2H5COOH concentration over OH minus divided by C2H5COO minus. Now, if you watch the Ka video, you already know what's going to happen here. We're going to make some assumptions in order to simplify this. We're going to say that, well, assuming that I had no hydroxide to begin with, that this in this is approximately equal. Pretty good assumption. It's not true. Okay, these will be slightly different, but they're close enough that it will not matter for a normal weak base. Okay, so we can assume that, and then we can also assume that the concentration of this original base will not change significantly from initial to equilibrium concentration. So the amount of base that I put into solution will be pretty similar to the amount of base I'll have at equilibrium once it's reacted with water. And the reason why is that for a normal weak base, so little of it reacts with water to make hydroxide compared to the amount that I initially had, that we can just kind of say, it's pretty much the same. Okay, so given that, we simplify it to this, right? Same as Ka, except now I have a B here instead of an A, and I have hydroxide instead of hydronium. So I have Kb is equal to my hydroxide concentration squared divided by A minus, and A minus just means my base concentration, okay? Because remember, we're dealing with Bronsted-Lowry acid base theory. So if HA was my generic formula for an acid, then A minus would be my generic formula for a base, because this can accept a proton to become the conjugate acid. So given that, I now can actually use Ka and Kb together to kind of figure out some stuff. So this is kind of neat. If I take a look at my Ka unsimplified and my Kb unsimplified formulas, and then I multiply them together, take a look at what happens. So just kind of to slow down, this right here is what Ka would work out to be, right? Product is hydronium and then the conjugate base. divided by the reactant of the original acid. Water doesn't come into here because water is a liquid, so it isn't part of the equilibrium expression. And then this right here is my Kb, where I have hydroxide multiplied by the conjugate acid, that would be in the products, divided by the base concentration. Now take a look at what happens if I try to cancel out some stuff from this. Okay, A minus cancels out with A minus, and HA here cancels out with HA here. So what that means is that I have Ka times Kb is equal to hydronium multiplied by hydroxide. Well, where have you seen hydronium and hydroxide before? Well, you've seen it in that that's the Kw expression. So that means that Kw is equal to Ka times Kb. And of course, it is also still equal to hydronium times hydroxide. But we can use this fact that Kw is Ka times Kb to find Kb. Okay, so if I have the Ka, which I do from the data booklet, then I can find the Kb for the conjugate base of that acid. And then Kw, of course, is your 1.0 times 10 to the negative 7, which is your water ionization constant. All right, so this is true for any conjugate acid-base pair. Now, I can't stress enough that this is for the conjugate base of the acid that I find in the data booklet, right? So I find this in the data booklet for the acid, right? And then the conjugate base of that acid. So on the same line in the data booklet, that is the base, and then I can use this expression to actually find the Kb. So we're going to go through an example, of course, so you can see this. So what is the base ionization constant for hydrogen carbonate ion? So hydrogen carbonate ion, I find it right here on the base side. Now be careful because it is right here, but that's as an acid. I want to find it as a base because it's acting as a base, and I want to find the base ionization constant. So I need to find it as a base. So here is the acid, here's the conjugate base, or the base I care about, and here's the Ka value for hydrogen, or carbonic acid, H2CO3. So if I want to find Kb, it's as simple as this. Kw is equal to Ka times Kb. So Kb is equal to Kw divided by Ka. So I'm going to have 1.0 times 10 to the negative 14 divided by 4.5 times 10 to the negative 7. So I'm going to go ahead and plug that into my calculator to see what the answer is. 1.0 second E negative 14 divided by 4.5 second E negative 7. And I end up with an answer of 2.2 times 10 to the negative 8 moles per liter. Oh, no, sorry, I'm doing a Kb. Zoned out a bit there. So this is my Kb value, 2.2 times 10 to the negative 8. And again, I can find that straight from my Ka. All right, so that's one example. So often what we have to do in these kind of base questions is we have to find the Kb first from the Ka, and then we can use that to figure out things like hydroxide. So here's another one. Maybe give it a try, right? I've got a Ka value there. Can you find the base ionization constant for hydrogen sulfide ion? So to figure this out, again, Kw is equal to Ka multiplied by Kb. So my Kb is equal to Kw divided by Ka. So I have 1.0 times 10 to the negative 14. I'll divide that by my Ka for hydrosulfuric acid, which is 8.9 times 10 to the negative 8. So if I plug this into my calculator here, 1.0 second E negative 14 divided by 8.9 second E negative 8, I have 1.1 times 10 to the negative 7. So this is my Kb for hydrogen sulfide ion, okay, that I found right here. And again, I found that from my Ka. Perfect. Another example, now we're gonna, oh, no, we're not. No, we're not gonna find hydroxide concentration. Okay, we're going to make up an example on the fly here because it's important we do at least one where we actually figure out hydroxide and POH for this. So let's just go ahead and say that I have a concentration of hydrogen sulfide ion of 0.50 moles per liter. So the next question is, okay, what would be the hydroxide ion concentration? So what concentration do I have for hydroxide ion? So let's go ahead and try to figure that out for this. So Kb is equal to hydroxide concentration squared divided by my base concentration, A minus. So I have hydroxide squared then is equal to Kb multiplied by my base concentration, A minus. So that means hydroxide concentration is equal to the square root of Kb multiplied by A minus. So I have for this 1.1 times 10 to the negative 7 multiplied by 0.50 and take the square root. So I have my full value here. Let's multiply by 0.50 for the concentration I made up on the fly. Now we got that. If I take the square root of this, I end up with an answer of hydroxide concentration then, OH minus, is equal to 2.4 times 10 to the negative 4 moles per liter. So now that I've got this concentration for hydroxide, I can figure out a POH. I'll do that over here because that's the only last little bit of area I have left. So POH is negative log then of my hydroxide concentration. So I have negative log of 2.4 times 10 to the negative 4 moles per liter. So let's go ahead and again use my unrounded value for this. Negative log of 2.4 second E negative 4. Gives me an answer of 3.62. So 3.62 as a POH. And then from there, I could actually figure out pH, for example, or hydronium concentration, whatever I need to find. All right, I feel like we need one more example for this because there's a bit of complexity. So let's do one more example on the fly. So I'm going to create a new page here, hopefully. Hopefully, new page. New page, come on, come on. No, that's undo and redo. There we go. New page. All right, so here's the example that we're going to do. What is the pH of a 1.20 mole per liter solution of acetate ion? Okay, so let's talk about the roadmap for this because this is quite an involved question. So what we're going to have to do in terms of steps is we're going to have to find a Kb from Ka. Then we're going to have to find hydroxide. Okay, using my Kb expression. Then after that, we're going to have to solve for POH. And then finally, we're going to have to solve for pH using the POH. So I would say that we got 4 big steps here that we're going to be going through. So I don't know. I think you should give this a try, okay, and then come back to this. But yeah, let's go ahead and go through the solution now. So if you haven't already, try it out. If you have, here's how we do it. So let's first of all find a Kb from the Ka. So I'm going to go back to my data booklet here, and I'm going to find acetic acid as an ion. So if I find acetic acid as an ion, or as an acid, what am I saying? As an acid here, CH3COOH, here's acetate ion as a base. So this is where I want to be looking because I need it to be a base. and then I take this Ka value and then change it to a Kb. Ka is for the acid, the Kb is for the conjugate base. So I have 1.8 times 10 to the negative 5. So Kb, let's first of all say Kw is equal to Ka times Kb. So Kb is equal to Kw divided by Ka. So I have 1.0 times 10 to the negative 14. Should have written down that Ka right away because I've already forgotten what it is. It is 1.8 times 10 to the negative 5. That's right. 1.8 times 10 to the negative 5. So let's go ahead and plug that in. 1.0 second E negative 14 divided by 1.8 times 10 to the negative 5. And I end up with a Kb value of 5.5 repeating times 10 to the negative 10. So 5.6 times 10 to the negative 10. So now that I've got that, let's solve for hydroxide. So let's do that over here. So number 2, I know that Kb is equal to hydroxide squared over my base concentration A minus. So I have my A minus. I'm trying to find my hydroxide. Let's skip ahead just a little bit here, do a little bit less of the algebra, and just go ahead that OH minus then is equal to the square root of Kb multiplied by my base concentration, A minus. So OH minus is equal to the square root of 5.6 times 10 to the negative 10 multiplied by 1.20 moles per liter. Not going to write the unit because I'm within an equilibrium expression. Wish I wouldn't have gotten rid of that, so we're just going to go second answer to get that 5.5 repeating back, times 1.20. And then we'll go ahead and take the square root of that. Second square root, my answer. And I get a value of 2.58, etc. So 2.6 times 10 to the negative 5 in significant digits moles per liter is my hydroxide concentration. So now that I've got that for 3, I'm going to solve for POH. So POH is equal to negative log of my hydroxide, OH minus. So I have POH is equal to negative log of 2.6 times 10 to the negative 5 moles per liter, right, to figure out my POH. So I'm going to go ahead and go second log, so totally wrong there, sorry, negative log, second answer. And I end up with an answer of 4.59 for a POH. I'm almost there, I'm so close to pH. 4.59. Finally, what I'm going to do is find pH, and I do that by taking 14 and subtracting 4.59 because I know that pH plus POH is equal to 14. So now that I've got that, let's go ahead and just plug in 14 minus second answer, and I end up with an answer of 9.41. So my pH is 9.41 at the end of the day. Does this make sense? Yeah, it's in the kind of the base range, right? It is basic. It's higher than 7 for a pH. It's not incredibly basic. When I take a look at acetate ion and how good it is as a base in terms of its relative position, okay, it's right here, so it's right in the middle, right? Here's my strongest bases down here. Here's my worst bases right here. So acetate ion, it's somewhere in the middle. So I mean, I think to me that kind of makes sense in terms of a pH value of what we get there. All right, so there's a full kind of how complicated things can get sort of example. So now hopefully that will help in terms of the questions in your workbook that are a little bit harder for you to figure that out. All right, that's KB Expressions. Have a good rest of your day.